Okay, so 1 o'clock today is September 16, 1 p.m. Okay, welcome back. And what was I saying? Yeah, it's going to be the same deal as last time. I am going to run over some terminology and some concepts. So you are going to be comfortable watching the other video, part 2. The reason for that is, as I said in the morning today, that video that I did last year, I'm really happy with that. And I had so many props and the setup was much better. I'm still in the process of moving my setup. So bear with me for maybe a week or so. But you will get the full benefit no matter what of what's going on here. Anyways, so let's just get a little tiny bit of a review from last time, just to make sure that we are on the same page. As far as multimeters, the multimeters, for the most part, we will distinguish the basic types: voltmeter, amp meter, and ohm meter. Voltmeter measures voltage, which is the electrical pressure between two given points. Then the amp meter measures current. You could call it a current meter, but for some reason phonetically sounds better as an amp meter, and that's how it stayed in our English terminology. And we also have the ohm meter. You could also call it a resistance meter because that's what it measures. It measures resistance. So when it comes to connecting a voltmeter to measure voltage across 2 points, how are we connecting that? Are we connecting it in series, parallel, or doesn't matter? Can anyone pipe in or say or type, just so we can so I can confirm that some of my points are getting across here. Anyone? Voltmeter. Okay, somebody said yep. Ethan. All right. It's getting across. All right, so how do we connect the voltmeter if we want to measure voltage across a resistor that is in the circuit? Let's say we're going to have a resistor. All right, okay, let me change the color. Color. Yeah. We have a resistor in a circuit. Here's another resistor. And it is connected to a power supply. Here's R1, R2. And if we want to connect this voltmeter, let's say, to measure the voltage across R2, are we going to put it in series with the circuit, or are we going to connect it in parallel with the resistor that we're going to measure? Series or parallel? Come on, one person say something. Parallel, but there's a question mark. Okay, so all right, series. All right. Okay, let's we are measuring the voltage across the circuit. So we're going to see, here's one point, and here's the other point, and we want to measure the voltage across these 2 points. So we're going to put our leads, one here and one here. There we go. Yeah, all right. So this is a parallel connection. We're tapping in parallel. And just as a piece of advice for you when you're going to, in your other subjects, when you're going to connect multiple circuits on something that's called a breadboard. And sometimes in some other subjects, you're going to connect things using the leads, especially when the electrical machines lab. And some of the circuits are going to get more complicated than the one that you see on the screen right here. So in order to keep sane and in order to be comfortable with connecting and assembling the circuit, try to establish the current path first. Let's make this one positive and that one negative, right? Here and here. So what is the current path here? The current leaves the positive, keeps going, keeps going, keeps going, and comes back right into the power supply. So here's our current path. If you had another resistor like that here, all right, then the current would be going as it is, leaving the positive, and then at this point some of the current is going to go this way and some of this current going to that way. So make sure you get the current paths set up first, and then after you do that, you are going to tap in with the parallel devices such as a voltmeter. Right? Now, because of the nature of the measurement that we're doing, and the idea of any measurement is to measure whatever you want to measure, okay? And without affecting the circuit. So what should we have, or basically what should we have? It's beyond your control. The meter is made the way it is. What is going to be the internal resistance of a multimeter once you switch it to be a voltmeter? So it becomes a voltmeter. What is going to be the internal resistance of the voltmeter? Is it going to be high, or is it going to be low, or is it going to be somewhere in between? Someone says low. Someone says low. Okay, let's stop right here. Let's say the voltmeter is not connected. It doesn't exist. It's just out of the picture. What is it that surrounds the resistor? What surrounds the resistor is air. Good, Olivia. So the resistance of the air is extremely high, to the point that for the labs that we're going to do, it is going to be considered as infinite resistance. So we want to, in order to not affect the circuit, we want whatever we connect as a measuring equipment, we want to also have a high resistance as possible because we are connecting it in parallel. The opposite of the high resistance would be a low resistance, and it would affect the circuit a lot if you connect just a piece of wire between this point and that point. So basically you're shorting that resistor at this point. So the circuit is affected. Yes, it is. Is it affected? Yes, it is. It's affected a lot. The whole behavior of the circuit is going to change. So let's just get rid of that. Okay. So when we are connecting the voltmeter in parallel with the load that we are measuring, we want the resistance to be as high as possible, because the idea is to take the measurement without affecting the circuit. All right. All right. Now, let's make my eraser a little bit bigger here. All right. So I'm going to interrupt the circuit right here, opacity. Yeah. I'm going to interrupt the circuit right here. Okay. And I'm going to connect the amp meter. And of course, the amp meter, the current has to flow through it in order to be measured. So we need to connect that amp meter. How? Series or parallel? In series, now we know. Okay, so here is the symbol of an amp meter with the big letter A. And we have the current flowing through it. But remember what was before the amp meter was connected? It was just a piece of wire. So what is the resistance of a piece of wire? For our purpose, it is very low. Ideally, the resistance of a wire should be zero. There should be no resistance. It should conduct the current as best as it can. So the resistance would be zero. So while we're connecting the measuring equipment in series with the circuit, then the internal resistance of that equipment should be ideally zero or very low. If you say zero, that's fine too. So that's what we're talking about when connecting voltmeter and amp meter. Okay, I'm going to show you something that some of you might already know. Just going to do that and bring that to the screen. Does anybody recognize this piece of software? Multisim. Looks like some of us already have contact with that. Multisim is a pretty good software, and I think I was telling that to the 8 o'clock class this morning. Please make sure, please check with the IT, and I'm also checking. I'm asking around because last year I heard that you, as students of our college, are able to get a student copy of that for either a very low cost or free. But don't quote me on that. Please check with the IT department in our school. Right? Information technology support, information technology office. If you Google the number, it's going to show. And now with all the construction going on, now it's in a B building, but it's a far B building there, and it's on the second floor. You can just walk up there and talk to them about your issues. Well, some of it. Okay. Anyway, okay. So let's connect an ohm meter. If you don't know how to use that, I'm just going to walk through this thing with you step by step. I was going to say something I forgot. Anyways, we're going to place a component on this thing here. So here is how we place the component. We go to the tab that says place, and we click that. And what do we want to place? We want to place a component. All right. Now this sub window shows up, and all groups here. For the groups, select all groups. That actually you don't have to select, it's going to come up as that by default. All right, now we want to place a resistor, so we're going to click on the groups, and we're going to choose the basic group of basic components. And if you go down here, you're going to see something like a resistor. All right, and over here you're going to see different values. You can choose a value, or you can just place a resistor of any value. Click OK, and okay, I'm going to zoom in. It's going to be attached to your mouse. I'm not pressing anything. Once I clicked OK, this thing gets stuck to my mouse. So until I click somewhere, and it's going to be placed. Okay, let's click it. Kaboom! All right, series 1, R1. Let's place another one, because if you don't close that window, it's going to serve you with being able to place as many of this. It's going to keep repeating placing. Okay, so let's click OK here, and let's click OK again here. All right, and let's close this window for now. See, by default, those resistors values are showing us 1 kilo, which is 1,000 ohms. Kilo is 1,000, right? The opposite of kilo is milli, which is, well, whatever the value is, times 10 to the power of -3. That will be milli. But kilo is whatever the value is shown, which is 1 for here, times 10 to the power of 3, which is 1,000. Okay, we can change the value either by right-clicking on it and calling up properties, or you can just double-click on this, okay? And it's going to call up the properties. Let's change the value. Here is the value 1,000. Let's just make this one here, as opposed to the other class, 1,500 ohms. So 1.5 kilo. There we go. Let's get this one, double click, change the value to 3 kilo. And that one here, let's make this thing 500 ohms without any suffixes. Click OK. So we here are our values of our resistors. Let's take a look if we can measure the resistance of each one of them. We can't see the resistance, we can't feel the resistance, but we can grab something that's called a multimeter. And here's the tool set on the right hand. Click on that, and again, the multimeter is right on top. If you click on it, it gets stuck to your mouse. So we can just place it right here above that resistor. Okay. And we can do the connections. Connect this little wire to this point of this resistor and this little wire to this point of the resistor. And double click on that. Double click on this meter to call up the display. Kaboom, click, click. All right, here's a display that belongs to this multimeter. Okay. Now, by default, it shows up as, it's set up as a voltmeter for the DC current or direct current. You can change it to alternating current or DC current. You can have it as an amp meter, you can have it as a voltmeter, or you can have a, you can use it as ohm meter, and we're going to leave the decibels alone for now. All right, so we set this thing as an ohm meter, and nothing is on the display. Well, because the circuit is not working yet. All right, let's see if I'm going to get an error again if I press that. In order to start simulation, you have to press that little play button. All right, it didn't come up with any errors. Basically what it is that most of the circuits that you assemble in multisim, they need to have a ground attached to some point of the circuit. And in this case, it just didn't need that. So it did not come up with an error. All right, so the display shows 1.5 kilo ohms because this resistor is 1.5 kilo ohms. Okay, let's stop the simulation, disconnect that, and connect these two resistors in series. What do you think you're going to have? 1.5 kilo plus 3 kilo in series. In series, we just add the resistors, so we should have 4.5 kilo ohms. All right, let's click the simulation. Oh, look at that, 4.5 kilo ohms. What do you think is going to happen if we connect the third one? Just for kicks, let's do that. I just stop the simulation because if you change anything in the circuit, you should stop simulation. Connect them in series. All right, so 3 kilo plus 1.5 kilo, that gives us 4.5 kilo, and this is half a kilo because it's a 500 ohms. So 4.5 plus half a kilo is going to give us 5 kilo ohms, right? Well, let's see, press play. Whoa, amazing, magic, eh? Okay, so when we connect the resistors in series, the total resistance adds, right? Okay, let's, as I said before in the class before, let's go crazy and connect those in parallel. I'm just going to connect those resistors in parallel, and I'm going to connect them just like that. Click, click, clickety, click. So all these three resistors are connected in parallel now. All right, let's see what the total resistance is going to be. I'm just curious, right? All the suspense. Press play. Boom. 333 ohms. Wow, this is 1.5 kilo. This is 3 kilo. This is 500 ohms. And the resistance is 333.333 ohms. Not this one thing. I'm going to show you. I'm going to tell you right off the bat. 1.5 kilo, 3 kilo, 500 ohms. Did you notice that the total resistance of all the resistors in parallel is smaller than, smaller in value than the smallest resistor? Let's confirm that theory. place a component. I already have the resistor. Place it here. Close that window. Change the value of it to, let's say, 100 ohms, which is going to be the lowest of them all. Just 100 ohms. 100 ohms. Bring it underneath here and make a connection. All right. Now, according to us, according to what we said before, what I said, the total resistance of these 4 resistors connected in parallel should be smaller than the smallest resistor. Okay, let's try. And it is. Look, it's 76 ohms. It's smaller. Always going to be. It's always going to be smaller. The total resistance connected of resistors connected in series is going to be bigger than the biggest resistor because we just keep adding them. And the total resistance of resistors connected in parallel is always going to be smaller than the smallest resistor. Why is that? We're adding resistors, but think about it. Just switch your gears in your wonderful brains and think about what is if we would just have one resistor. If it's just R1, what do we have? The current path goes only through, like if these don't exist, R2, R3, R4, if they don't exist, there's only current pathway because the multimeter, when you switch to ohm meter, it's introducing its own power, a little tiny bit of power just to push the current through the part so we can calculate the resistance. How does it calculate the resistance? We bring up the screen here, clear the board. All right, when you're adding the resistors in series, the total resistance is good. Okay, so what's the formula that is being used? I'm going to introduce you to, I'm going to give you a heads up on the Ohm's law. Remember this word, VIR, VIR. Huh? And then all you just have to do is do that. Okay. Voltage equals current, which is the symbol of I, times the resistance. If we want to isolate the resistance out of the equation, because now the voltage is isolated, we need to do something to the both sides of the equation in order to keep the equal sign true. Right? What do we have to do to this part of this equation in order to isolate I? We have to divide it by I. So in order to keep the equal sign true, you have to do the same thing to the other side. So IR divided by R, we're going to cancel the I's and we're going to end up with R. And here is our equal sign, and you have to do the other side, same thing. So we have to divide voltage by the current. And this is how this ohm meter calculates the value of the resistance. It has a little brain inside that does that. So how is it that the total resistance of resistors in parallel is smaller than the smallest resistor? Well, let's do it the other way. R1, R2, R3 don't exist. We just have 100 ohms connected to oh, we have to stop that. Okay, that's why it doesn't let me do it. We only have R1 connected to this circuit, and basically the ohm meter acts as a power supply, supplying a little power so we can push the current, so we can measure the current, and based on that, it's going to calculate the resistance. So now we have current pathway going this way. What is surrounding that in parallel with that, with the resistor, it's the air. And the resistance of the air is very high. So, well, if you see the resistance of the air, which is infinite, and it's in parallel because it just surrounds the resistor, it's basically connected in parallel with the resistor number 4, the total resistance is 100 ohms, which is, well, equal to the smallest resistor that is connected. Right? Now, let's see if we connect the biggest one of them here. We connect 300 ohm, 3 kilo ohms, which is 3000 ohms to that. Well, we have in parallel, we have the 100 ohms, we have the A, which is huge resistance, and then we have 3 kilo, which is also not a small resistance, not a bigger, but it's bigger than that, but it's smaller than the air, which means that connecting that resistor, even though if it's bigger than that, it just provides one more pathway for the current to flow. So before, the current was pushing just through this pathway, and now the current is pushing through that pathway, and some of it can go still here. So it is easier for the current, the total current, to flow, which means the total resistance is less. It's less than the lowest resistance because that was the lowest, and then we provided another pathway for the current, so the total resistance is going to be less. And if you keep adding, it's just how it works. Right? All right. Erase the lines here. I'm going to get rid of things. Now let's see if we can do some voltage measuring. Oh, I'm going to give you the formula for that. If you want, where's my Photoshop? There it is. Oh, erase the board. Okay. So when you're adding resistances in series, yeah, I'm just quickly drawing the R1 and R2 and whatever. Let's call this thing Rn for whatever the final destination is going to be. So the resistance total, or the total resistance of this whole circuit between this point and this point, is going to be, or it is, R1 plus R2 plus whatever the number of resistors is here, plus Rn, which would be the last resistor, and that is basically a simple calculation as that. Now, that's the series. Okay. If we were talking about parallel, resistor, yeah, I'm just drawing this thing quickly, and here are the connections, here and here. Here's 1 point, and here's 1 point. So here's R1, R2, R3. Okay. What is the total resistance between these 2 points? Right, this one and that one there. Well, the formula is, in its simplest simplicity, 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, and how many of whatever the resistors you got, you're going to keep adding that. So that's the formula. There are different variations of this formula, but this is basically, I'm giving you heads up on that. You will study this thing in other subjects, which is going to be more than one subject, but I'm introducing you to that. I have to explain this thing to you a little bit because I'm showing you the multimeters. All right, so let's measure the voltages. I'm going to spread those resistors apart a little bit, and let's keep that R4 on the side for now. You know what? I'm just going to get rid of it, so get rid of the pollution. All right, let's connect the series circuit and measure some voltages. Power supply. Do I have a power supply? Not yet. Place, component, And we're going to go to sources. Here it is. And we're going to go power sources. And first I'm going to go replace ground because we will need a ground. So I'm just going to keep it on side here. And we're going to go DC power. And that looks like a battery sign here, place there, and just like that. I'm going to click on that and press Control R, like Control Romeo R, Control R in order to rotate this part to the orientation that is more comfortable for me. And now let's place one more thing. Let's place a switch. So place a component, and let's go to the all groups. So everything is just as a default. And over here is a search window. We're going to type SPST. SPST stands for single pole, single throw, single pole, single throw. What happens if we want a single pole double throw? Single pole double throw. Well, here is a single pole, here is a double throw. We can throw this pole one way or the other, right? So it's a single pole double throw. Let's try something else. Double pole double throw. Oh, well, we have a switch that has two poles, and we can we can put it in the this way or that way, so it's a double throw. But we are interested in a single pole single throw. Connect the switch or place the switch right here and close that. Now, you can see the key equals space, which means if I press the space, it's going to operate the switch. Cool, eh? Now what you can do is you can call up properties by double clicking or right clicking and choosing properties. And see, it says key for toggle and it says space. Well, I can choose any key of the keyboards to make that thing operational, to assign to that switch. Let's say I'm going to go Q, well, and click OK. See, now it says Q. That means, like say, if I copy this switch, here, there's both Q. So if I press Q, both of them are going to operate. But I can change this from Q to, let's say, W. All right. So now Q is going to operate this switch and W is going to be operate that. So I can operate them independently. That's the idea of the multisim, all right? But what I'm going to do is I'm going to call the properties and I'm going to go to the display tab here and I'm going to choose this here, use component specific, don't show everything as you please. Let me choose what I want to see, and I want to see nothing. Just to get rid of the graphic pollution, now we have a clean switch for our purpose. All right, we got the ground here. So let's connect from power supply to the switch, from the switch to this resistor R2 here. From R2, let's go to R1. Let's go to here, and from here, red thing connected to the blue thing, and we have a closed circuit. Now, when we press the play button, we have this thing up. Well, here, okay, we have the current flow. Can you see the current flowing? Of course you can't. That's why we have the measuring equipment. Let's stop the simulation, connect the ground here, open the switch, and let's connect some multimeters here. So I'm going to choose one multimeter, press it over this resistor, grab another multimeter, press it over this resistor, grab another multimeter, and press it over this resistor. And you know what? Let's just do something a little bit more here. And I'm going to first, I'm going to rotate that. So I chose that, I selected that, Control R. Again. All right, good. And we can connect the amp meter to the whole circuit. Now let's call up the displays. Double click, double click, double click. Oh wow, let's connect the multimeters. Oh, come on, stay there. Be nice. Make it nice and pretty. wiring hygiene and drawing hygiene is important when drawing, especially when the circuits get more complicated. So let's start practicing the visual hygiene on this thing. We have all the three multimeters connected in parallel, and then we have one in series. So these are going to be the voltmeters, and this is we're going to make this one an amp meter. Okay, call up the displays, double click. That one goes here. Just so we can fit that. That one goes here. Here. This one goes for that one. This one goes with that one. And this one goes with that one. Let's make sure the setup is good. Voltmeter, yes. DC current, yes. Voltmeter, DC, yes. Voltmeter, DC, yes. Amp meter, oh, amp meter, DC. All right. So let's start simulating the circuit. Press play. And what do we have? We haven't pressed the switch yet. All right. So what do we see here? 359 point something 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 volts. Then there's another number, something volts. There's another number, something volts. Do you know what that is? That little U beside the volts? It's not actually U, but we don't have that Greek letter. Micro, there we go. So it's actually it is actually the letter mu, Greek letter. There you go. Greek letter mu, and it looks like this. It looks almost like U, but it just has that extended limb right there. But because we don't have that letter, Greek letter mu in our keyboard, so when we write our units, it's going to be like that. It's going to show up this way here, just like U. But it's supposed to be the Greek letter mu, like a mule, mu. All right. So micro is the opposite of mega. And what is mega? Mega is whatever the value to the power times 10 to the power of 6, which is 1 times 10 to the power of 6 makes it a million. Well, if you go micro, it's whatever the value is to the times 10 to the negative 6 instead of 6. So it's the opposite of a million, which is 1 millionth. Micro is 1 millionth. All right. So it's a very little voltage. Well, because so the multisim is simulating the noise that is on that resistor. Where does the noise come from? Well, we have all kinds of energy happening around us, from the radio waves, from radiation, from the TV, keyboards, mice, whatever else. It's all combines, and it has a little bit of an electrical noise happening, right? So that's what it's picking up. Um, so let's close the circuit. Of course, the nano is times 10 to the negative 9, so it's like 1,000 millions, but the opposite, 1,000 millionth nano. Okay, so very little happening. Let's close the switch. Bam. And what do we have here? We have across this resistor 7.2 volts. Across this resistor we have 3.6 volts, and across this resistor we have 1.2 volts, and the total current is 24 milliamps. Well, what do we have here? If you get your calculator and you add 7.2 plus 3.6 plus 1.2, and as multisim, whenever I move mouse, multisim moves on me. So keep asking multisim, please take care of that. It's annoying. Anyways, let's get a calculator. And what do we have? Let's make it smaller here. 7.2, just to prove it. 7.2 plus 3.6, 3.6 plus 1.2. Let's get the drum roll. Boom, it's 12. What do we have here? 12 volts. Cool. And you can notice that the bigger resistor, the bigger voltage drop is going to cause. I had the right answer, but wrong answer. uh, no, it is 12. Yeah, here's 12. Oh, you're somebody else. You're Nicholas. All right. Excuse me. So notice that um, the bigger the resistor in value, the bigger voltage drop it is going to cause. And that mouse, as I move my mouse, multisim is moving with me. Okay, I can't do that. Yeah. So I'm just going to do it here like that. You see, here is 3 kilo ohms, which is 3000 ohms, has 7.2 volts on it. And here's just 500 ohms, and it only has 1.2 volts on it, right? So it's, you know, the magnitudes of the voltage are going to be proportional to the resistance, and it makes sense, right? It resists less, the less pressure is going to be across it. Right? And the total current, remember the formula? There. How do you calculate the current? From the VIR formula. VIR. Here's the current. Here's the resistance. Here's the voltage. V equals I times R. Okay. Let's get the current out of it. So we have to divide both sides of the equation by R. So the current I equals divided by R and divided by R. So the current here, V over R. Okay, total resistance. What do we have as total resistance? Our total resistance in the circuit is 3 plus 1.5 plus 500 kilo. That's 500 ohms, kilo. So 5,000 ohms we have. And the voltage is 12 volts. So we could just do this. V over R equals 12 volts, and always write the units. And I not only write the units, but I put them in square brackets over 5 kilo, or you can put 1000, what is ohms, omega here, and put the units in square brackets just to make things clean. Oh, calculator, 12 divided by 5,000 equals, well, 0.00024 of an amp. So let's make it how many milliamps? We move this decimal point 3 points. So 1, 2, 3, 2.4 milliamps. 2.4 milliamps. Okay, it works. Wow, magic. All right. One last thing I'm going to show you, because on that video I'm showing you how to measure the diodes. Because when you switch, it doesn't have this function here, but your multimeter does. It has the diode tester. When okay, let's stop that. Here, clear the whole board. Let's place a component. Place component, and we're gonna go diodes. And diodes virtual. Oh, it's a diode. Okay, it's just a simple diode. Oops. Here, escape. Close. We have a diode that says D1. All right. Place component basic. Well, let's get power source. Sources. DC power. Let's get here, and let's get a ground as well. This one is not going to let us operate. What else do we need? We need some sort of a resistor. Okay. So that goes under basic components, resistor, kaboom, kaboom, and close that. Let's make this resistor something like maybe 330 value, 330 ohms. Okay, let's do that. And let's make this one the power supply. Let's make it just okay, 5 volts. See what happens. Okay, so here we have a 5 volts. Control R to and there we go. And here we have a ground, and place a switch component. All groups, SPST. We already have it. Kaboom! There we go. Let's clear the switch of the graphic pollution here. Now we have something to go with. All right, I'm just gonna bring this thing a little closer. Connect, 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 and we want ground. Well, let's see what happens if we don't connect the ground here. See, it just gives us an error, right? So stop that, connect the ground, press now, no errors. This one wants ground to be connected. Okay. All right, let's get a couple of multimeters. A multimeter here, a multimeter here. Connect that across the diode. And this we're going to connect across the resistor. Good. Call up the displays, double click. That's the display for this meter, and that's the display for this meter. Double click on the meters. And we got voltage, DC, voltage, DC. All right. How is it that diode works? I'm going to start simulation here. So now we have very little voltage here, just a noise across the components because the switch is open. There's no current flow. So diode is a semiconductor that conducts only one way, and it has to be polarized the proper way. So this is anode part of the diode, and this is the cathode part of the diode. Anode is positive, cathode is negative. How do you remember which is which? Well, it's a very simple thing. In school, you just want to get, what's the best mark that you want to get? A? Well, the best mark is A plus, all right? Anode starts with A, so A plus. So anode is positive. That's how you remember. Anode is positive, cathode is negative. If it is polarized this way, it is going to make the current flow. If you flip the diode the other way, you polarize it in reverse, then the current is not going to flow. It's going to give you high resistance, just like an open circuit. Unless you crank up the voltage so huge that you're going to burn the diode, and yes, it's going to conduct for a little bit, like a split second. All right. Oops, close that. Stop the simulation. Let's just get one more. Of course, we're going to get the amp meter as well. Why not? Eh? We're doing the metering here. Make it pretty. There you go. Visually better. Call up the display by double clicking on the meter and make it an amp meter DC. All right, so we have the displays, Okay, now what happens with the diode? Diode is going to conduct one way. However, it is going to resist it at first. If you keep raising the voltage across the diode, it's not going to conduct. It's not going to conduct until it reaches certain voltage, and that is called the forward bias voltage of a diode. And in a silicon diode, if this is a silicon diode, the forward bias voltage is 0.7 volt. That's it. When the diode conducts, it is always going to have 0.7 volts across it and nothing else. You can raise the voltage here. Remember when we did the resistors, this plus that plus that plus that equal the total voltage. So this is always going to be 0.7 no matter what. And the rest of the voltage is going to be here across this resistor once we raise the voltage. Let's prove this idea here. Now, here's the silicon diode. The germanium diode is the forward bias voltage is 0.3 volts. If you get your multimeter and get just a regular rectifier diode, 1N4007, 4001, all those 400s, and you switch your meter onto the diode tester, and if you put the leads in a way that it forward biases, because the diode tester also, just like an ohm meter, introduces a little bit of a voltage across the leads. So that's why you never should measure the diode when it's in the circuit. Also, you have to isolate. So if you forward bias that diode with the meter leads, you're going to have some number displayed, and people wonder, what is that number? Well, it is going to show you the forward excuse me, show the forward bias voltage. If it's a silicon diode, it's going to show 0.7. If it's a germanium diode, it's going to show 0.3. Now, there's also those light emitting diodes, popularly called as LEDs. They also are diodes, but not only they behave like a diode, but also they emit light if current goes through them. How do you accomplish different colors with the diodes? Well, the companies that make them out of different materials, and different materials combined together, they produce different forward bias voltage. And that's what I show on the video that you're going to watch. You can Google the forward bias voltage on LEDs, or LED forward bias voltage, or LED forward voltage. The screen is going to light up with a whole bunch of tables showing you what the forward bias voltages should be. And they are different for different colors because different materials are being used. Okay, so now the LEDs require slightly bigger voltage than the silicon or germanium diode. So the voltage that is being put out by the diode tester might not be enough, and you could get a false reading. And that's how I am showing you on that video. Well, let's just prove that 0.7 volts here. Start the simulation and turn the switch on. All right, so we have 12.9 milliamps here. What do we have? Oh, look, 721 millivolts. So if you look 1, 2, 3, if you shift the decimal point 3 times left, you're going to get the volts. So yes, it's showing 0.7 volts plus some change. Okay, then the rest of that is going to be on this resistor. And if you add these two, you're going to get 5 volts. All right, let's just prove that the diode, all right, is going to keep its forward bias voltage because it's a silicon diode. So we're going to stop the simulation, raise the voltage here. Okay, value here. Let's go, well, raise 1 more volt. So that should give us 1 more volt here on the resistor. So instead of 5, let's make it 6 volts. Okay. Simulate. All right. We got 0.7 volts instead of 4 and change. We get 5 and change. All right. So the diode is always going to keep the voltage the same. All right. Okay, so this is the end of this lesson here. Now I'm going to ask you to watch this video here. This is part 2, and it's not going to be always like that. The beginning of the term is always harder, just like the Tom Hanks Castaway movie. Remember, he was trying to get on the ocean and he couldn't get through the waves, so he had to do a little bit extra paddling just so he could get the smooth sailing. That's the same thing. That's what happened. Life is hard, but I just want to give you as much as possible so you get the substantial information once you leave the school. All right, so here's our class portal in the announcements. Scroll down. Oh, YouTube playlist here. Click on that. And it's this video right here, safety multimeters part 2. Here's the multimeters part one with the kind of explanations before that. And the second explanation, that was the one that I did at 8:00 a.m. This one is going to be right underneath that. It's going to be this one right here, but we're doing it right now, so it's not there yet, right? Here is this video that I need you to watch. And during this class that I did, just during this presentation that I did right now, I made it for you. So I made it easy for you. So you can understand this video better rather than without what I just showed you right now. Okay. We are smooth sailing with the labs right now. Just a reminder, we absolutely need to have our PPE for the labs, because if you don't have the personal protective equipment, we are not allowed to let you in that room. If we let you in that room without the PPE, I'm going to get in trouble. So you know what? I like my job. So that plus, the main thing is that PPE is PPE, right? Personal protective equipment. You need that in that room, right? So then, which is safety boots, hard hat, and safety glasses. Section 6 has lab this weekend, right? Or Wednesday, sorry. Let's see here. Our class portal. That's our class portal. Okay, that's the main page for our class. Where's the schedule that I posted? Section 6. Section 6 right here. The lab is Wednesday, September 21st, and it's with Mrs. Hashemi. Okay, so that's section 6. Section 3, Thursday, 1 to 3 p.m. with me, and section 1 also Thursday, 3 to 5. So that's the schedule for this next week, lab 1, and that's pretty much it. Yeah. Also, I am asking you to bring yourself a padlock to the lab, because we are not supposed to leave bring our school bags to the room. We are not the only ones there. There are many people. This room gets crowded with different classes. Yeah, you're welcome. With different classes, and nobody brings their school bags. Just whatever you need, just like you're going to work. So there are temporary lockers around the corner from the lab, and that's where we leave our school bag, our jacket, and you put a padlock on it for the time being that you're in a class. And then when the class is done, you go to that temporary locker, remove your stuff, and remove the lock so other people can use that locker temporarily. All right. So bring that padlock. And we're going to be really strict on that. What if we have our own locker? Well, if it's close enough, that's fine. I mean, you don't you don't have to just leave your school bag in your locker. Right? Excuse me. Right? It's just it's just extra convenience, to have that. Mine is in the building. Yeah. So you decide. But just don't bring a school bag to to the room. Okay. That's pretty much it that comes to my mind. As far as any questions, I always have to say, is there any questions? Of course, if nothing comes to your mind right now, you're always welcome to send me an email, and I'm doing my best to reply to them as soon as I can. All right. Okay, so that's it for today. You have 1 minute to go, so you can have all this time to spend before your next class, if you have a next class after that. Thank you for your attention, and I see you next time I see you. Bye.